In this video, we're going to continue our discussion of global data flow analysis by taking a look at how global constant propagation works in detail. To begin, let's review what the conditions are to do global constant propagation. So to replace a use of a variable x by a constant k, we have to know the following property, that on every path to the use of x, the last assignment to the variable x is x equals the constant k. Okay, and this has to be true again on every path to the use of x. Now, global constant propagation can be performed at any point where this property holds. What we're going to look at in this video is the case of computing the property for a single variable x at all program points. So we're going to focus on one variable x, and we're going to compute whether it's a constant at every program point. It's easy to extend the algorithm to compute this property for all variables. One very simple but inefficient way to do that is to just repeat the computation once for each variable in the method body. The way we're going to compute the information that we want is to associate one of the following values with the variable x at every point in the program. And let's start with the last one here. We will assign x this special value here, which is pronounced top, if x is not a constant. So if we can't figure out whether x is a constant at a particular point in the program, then we'll just say x is top at that point. And this is going to be our safe situation. It's always okay to say we don't know what the value of x is. And when we say that x has the value top, and we were essentially saying we don't know whether x is a constant or not at this point in the program. X could have any value. All right? Now, another possibility is that we will say that x is some constant c. Okay, so this is a particular constant, and if we say that x is a constant c at a program point, that means, in fact, at that program point, we believe, or we have proven, that x is always that constant. Now, there is a third possibility, which is not immediately intuitive, perhaps, but as we will see, plays a very important role in algorithms for global constant propagation, in fact, in all global data flow analyses, and that is bottom. Okay, so this value is pronounced bottom, and intuitively, the idea anyway is that it's kind of the opposite of top. All right, and the interpretation of bottom is going to be that this statement never executes. All right. So when we don't know whether a statement is even executed at all, we will say that x at that point has a value bottom, meaning that as far as we know, that point in the program is never reached. It doesn't matter what the value of x is at that point because that statement never executes. All right, so we're going to assign x one of these three kinds of values, either bottom, some constant, or top. Let's begin by working through an example by hand, and our goal is going to be for every program point to decide whether x could be a constant, definitely not a constant, or whether we think that statement might not ever execute. Okay, so execution will begin at the top of this control flow graph, so this is the entry point, and before execution begins, we don't know anything about the value of x, so I'm not making any assumptions about what code came before this basic block. And so to be safe, I will say that at this point, x has some unknown value. We don't know what the value of x is. It could be anything. So x is equal to top is the property that we want on entry to the first basic block. Now, after the assignment x equals 3, you just indicate there what point we're talking about. So after the assignment x is equal to 3, definitely we'll know that x is the constant 3. All right, now there's something here that's worth pointing out, which is that our program points, the points that we're attaching this knowledge to, or these facts to, are in between the statements. So when I say x is equal to 3 at this program point, what I mean is that after this assignment has executed, x is equal to 3, but before this predicate of the conditional has executed, I know that x is equal to 3. Okay, so program points are in between statements, and there's a program point before and after every statement. All right, so the next thing that happens is this conditional branch. Notice that the branch doesn't update x, doesn't even refer to x. So after the branch executes, we'll definitely know that x is still equal to 3 on both branches. All right, now let's do the right-hand branch. The next thing that happens is an assignment to y. That will not affect the value of x. So after the assignment to y, we'll still know that x is equal to 3. All right, now let's take a look at the left-hand branch. So the first thing that happens over here is another assignment to y. Well, that won't affect the value of x. So after the assignment to y, we'll know that x is still equal to 3. And now comes an assignment to x. All right, so after this assignment happens, at this program point, we're going to know that the value of x is different. We're going to know now that x is equal to 4. All right, so now after this statement, we know x is equal to 4. And after this statement over here, we know x is equal to 3. All right. Now, what do we know then about what happens before this statement? Okay, the a equals 2 times x. And I just want to point out here, I said that there's a program point before and after every statement. And so this program point here, which is before this assignment to a, is different from the program points that are after x is equal to 4 and y is equal to 0. So intuitively, after x is equal to 4, we know that we're still on this path over here on the left. And so we know that x is equal to 4. And over here, after y is equal to 0, we still know that we're on this path as x equal to 3. But when we reach the point before a equals 2 times x, we no longer know which path we're coming from. This is the point of the merge of these two paths that both lead to this statement. And what can we say about the value of x here? Well, there's no constant that we can assign to x because on one path x is 3 and on the other path x is 4. And so what we have to say here is that before this assignment executes, x is equal to top. We don't know what the value of x is. Another way of saying is we don't know that x is a constant. All right? So after the assignment to a executes, that doesn't affect the value of x. We will also have that x is equal to top. Now notice that once we have the global constant information, once we know for every program point what the state of x is, it's going to be very easy to perform the optimization. We simply look at the information associated with the statement, and then it will tell us whether x is a constant when that statement executes or not. And if x is a constant at that point, then we can replace that use of x by the constant. And the crucial question, of course, is how do we compute these properties? So we did an example by hand, but how, in a systematic fashion on an arbitrary control flow graph, do we actually compute these properties for x for every program point? Now we're ready to talk about data flow analysis algorithms, and there's one basic principle that you see in all of these algorithms that's worth mentioning right away. And that's that the analysis of a complicated program can be expressed as a combination of very simple rules that relate the change in information between adjacent statements. So we're just going to focus on local rules, and the way we're going to build our global data flow analysis is actually by a combination of rules that look only at a single statement and its neighbors. The idea behind the rules is going to be to push or transfer information from one statement to the next. And so for each statement S, we're going to compute information about the value of x immediately before and after S. Remember, that's where those are the program points that we want to attach information to. So in particular, we're going to have a function C that stands for constant information. And C will take 3 arguments. It takes the name of the variable, x. It takes the statement that we're talking about, the particular statement in the program that we're looking at, and then either in or out. And this is what distinguishes the value of x before S executes versus the value of x after S executes. We're going to be defining a set of transfer functions that push information or transfer information from one statement to another. And in the rules for constant propagation, we need to talk about a statement and its predecessors. So we're going to say that every statement S has some set of immediate predecessors P1 through Pn. All right, so these are the statements that lead in one step to the statement S. Let's do our first rule. So we have a statement S, and it has some set of predecessor statements, P1, P2, P3, P4. And the situation that we're interested in here is let's assume that x is top at the program point after one of these predecessors. So after some predecessor, doesn't matter which one, if it happens that x is top at the program point after that predecessor, well, then x has to be top before the execution of S. Okay, so that's what this rule says. It says if the out of any predecessor for x is top, then the in of s for x is also top. All right, and this makes sense. It says that if we don't know whether x is a constant on some path that leads to s, well, then we don't know that x is a constant at s, because for all we know, execution came from that particular predecessor, and so we can't make any prediction about whether x is a constant before s executes. Now let's look at another situation. Let's say that x is some constant c after the execution of some predecessor, and that after another predecessor, a distinct predecessor, x is a different constant d. So d is not equal to c. Well, then, what do we know about x at the program point before s executes? Well, we don't know anything. X has to be top because we don't know which constant s will be, since we don't know which path will reach s at runtime. And this is the situation that we saw in the example we did by hand. Another possibility is that the predecessors all agree on what the value of x could be. So let's say that we have a predecessor here, and that after it executes, x is known to be the constant c, and x is known to be the constant c after this predecessor, and x is known to be the constant c after this predecessor. There's one other possibility. Let's say that after this predecessor over here, all we know is that x is bottom. Okay? And so what the rule says is that if we have this situation where either x has the property bottom after a predecessor, or all the predecessors agree on the particular constant that x could be, then before, at the program point before s executes, we know that x is guaranteed to be the constant c. And if you think about it for a second, it's easy to see why this is correct. First of all, clearly, if we come along one of the paths where x is known to be the constant c, since they all agree, then when we get to s, x will definitely have the value c. What about the bottom case? Well, remember what that means. That means that this statement is never reached. So there's some predecessor p here which never executes, which means that if p never executes, then we could never reach s along this path from p. So the only paths that will reach s are the ones where x is known to be a constant. All right, so that's why it's okay in this situation to say that if execution reaches s at all, it's guaranteed to reach it in a state where x is the constant c. One last possibility is, let's say that x is bottom for all the predecessors. Okay, and what does that mean? Well, that means that every predecessor of s never executes, that they're all unreachable. And therefore, if every predecessor of x never executes, s itself can never execute, and so we can conclude that on entry to s, x is bottom. The first four rules that we just looked at relate the out of one statement to the in of the next. We also have to have rules that relate the in of a statement to the out of the same statement. So we have to push information from the input of a statement to the output of the same statement. So once again, there are several cases, and let's take a look at an easy one first. If x is bottom on entry to s, at the program point before s, well, that says that s is never reached, that s never executes, and therefore x will be bottom after s as well. So if the program point before s is never reached, the program point after s definitely can't be reached either. Another possibility is that we're assigning x the constant c in a statement. In that case, the out of the statement is going to be equal to c. All right, so it doesn't matter what the state of x was before the statement. After we execute the statement, x will be the constant c. And I should say there is a conflict with the previous rule. Okay, it could be that x is bottom before the statement. So Rule 6 has lower priority than Rule 5. So if we could say that x is bottom after the statement, we would prefer to say that. So Rule 5 would be applied first, and then if Rule 5 does not apply, so if x is some other constant d or x is equal to top, then we would apply this rule, and we would conclude that x is the constant c afterwards. And that makes sense. If x is d or x is top, that means that control as far as we know, can reach this statement. And then what we're saying here is that, well, after the execution of this statement, if control can reach this statement after the execution of it, x is guaranteed to be the constant c. Another possibility is that we have an assignment to x, but the right-hand side is more complicated than a constant. So this case is for everything except a constant assignment. Okay, so this f here just stands for some more complicated expression than just a simple constant. And in this case, we're just going to say we don't know what the value is. We're not going to try to guess what the result of that computation is, and we'll just say that x is equal to top. We don't know what the value of x is after the execution of this statement. And once again, Rule 5 takes precedence. So if Rule 5 applies, then we would apply, then we would use that rule instead of Rule 7. But if control can reach this statement, so up here x is equal to some constant c, or x is equal to top, then we'll apply Rule 7 and conclude that x is top after the statement. And finally, Rule 8, another possibility is that we're assigning to some variable other than x. And in that case, if x was equal to some value k before the statement, then we just keep that value. Okay, so whatever x was before the statement, bottom, a constant, or top, if the assignment is to some other variable other than x, then x will have the same property after the statement executes. Now we can put these rules together into an algorithm. For every entry point, for every entry statement to the program, we're going to say on entry that we don't know anything about the value of x. So the program point before that entry point, we're going to say that x has an unknown value top. And then everywhere else, we're going to say that the value of x is bottom. Okay, and this is actually important. So what this intuitively is doing is it's saying, well, so far as we know, except for the entry point to the program, which can definitely be executed, we don't know whether any of the other statements in the control flow graph are actually ever executed. And so we're going to assume initially that they're not. And we're just going to say that x has the value bottom everywhere except at an entry point. And now what we're going to do is a kind of constraint satisfaction algorithm. We're going to pick some statement that doesn't satisfy one of the rules, 1 through 8, and then we're going to update it using the appropriate rule. So we'll look for places in the control flow graph where the information is inconsistent according to the rules, and then we'll update the information to make it consistent with the rules. Let's take a look at our example again. So we're going to start out by saying x is equal to top at the entry point, and then we're going to have all of our other program points, and let me indicate them here. Okay, so these are all the other program points that we have to be concerned with. And then again, there's a program point before and after every statement. And we're going to say that x is equal to bottom for all of these. So again, what this means is that so far as we know, control doesn't reach any of these points. We have not yet proven to ourselves that any of these statements can execute. And now we just look around in the program and try to find places where the information is inconsistent according to the rules, and then we update the information. So let me switch colors here. So when we begin, the information is actually consistent everywhere except at this first statement, because if x is top before and we're assigning x the value 3, well, then we should not have x is equal to bottom as the result. In fact, this should be x is equal to 3, should be the appropriate information here. And once we update that, then we see that this next statement is inconsistent, because now we know this statement is reachable. We have a statement here, and we're concluding that the point after is not reachable, which is not correct according to the rules. So I believe that this is an application of Rule 8. We have a statement here that doesn't refer to x, and so whatever the value of x was before the statement becomes the value of x after the statement. So that becomes x is equal to 3. And then now we can see that this information is inconsistent. The out of the statement here is not consistent with the in of the statement here. In this case, it's just one predecessor, and so the values should be the same. So x should be 3 at this point, and similarly, x should be 3 at this point. Here we have an assignment to a variable other than x. That should information should be the same before and after the statements. Same thing here. Now we have an assignment to x. The point before that assignment is reachable, and so since this is a constant assignment, we should know that x is that constant after the assignment. So here again we have a in and out issue. So the out of this statement is not consistent with the in of this statement. So this is going to have to be updated. But now, what should this be? Well, we have two inconsistent predecessors, and so this has to be top. And then finally, an assignment to x. An assignment to a variable other than x. So the information should just propagate across, and that statement is updated like this. So now x is known to be top afterwards. And now, if we look around at all the program points, we see that all the information is consistent. All the rules. If you check whether the information before and after a statement or across a statement, or between predecessors and successors is correct, it's correct everywhere according to the rules, and so we're done.